Okay, Assalamualaikum. So today we'll be discussing a little bit about component failure and how it can be avoided. I'm gonna show you a simple example of a component and how it fails and what are the ways that engineers normally do to avoid it. Okay, let's start. Let me just first pick a right color. Okay, so I'll be drawing this component right here. Okay, okay. I'm not really a good artist, so please don't judge my drawing skills that much because, yeah, I'm really bad at drawing, so I hope you can forgive me for that. Okay, so add a hole here and add a hole here. Okay, what I've just drawn here actually is a common component that you'd see in your chairs and tables or your cabinets whenever you're assembling them. It's called a bracket. Okay, so let me just write that down. B-R-A-C-K-E-T. A bracket. Okay, so we call this a bracket because it's meant to fasten. Okay, fasten or secure things, actually, rather fasten, right, or secure. Oops, let me just write it correctly. I didn't spell that correctly right there. Secure components, right? To secure components, actually, to secure components in an assembly. Secure components in an assembly. An assembly is a very large, how do I say this? It's not really a part, but it's more like an object. For example, you can consider your chair, your table, okay, or your cabinet as an assembly, okay? All right. So when we use this bracket, normally there are two holes which I've just drawn here actually, and this is where we would fit our screws. Okay, this is where we would fit our screws. Right, so you can hold the components in place. Okay, so these are holes for screws, by the way. All right, let me draw in the side view so it'll be easy for you to understand it. So okay, here is it in side view. Okay, and I'm gonna put a blue color to show the screws. Okay, so we usually put the screws here. All right, and another one here. Okay, now when the screws are in place with the bracket, there is something interesting actually. They exert a force on the bracket. Okay, they exert a force. I'll be marking in orange color to show the direction of the force. Okay, they exert a force on the bracket. Now this force, okay, we will call it as contact force. Okay, we'll call it as contact force. So what is this contact force that we're talking about here? So this contact force is actually a result, okay, of if you have two objects. Okay, I'm going to draw one of them in blue and another one in white. Okay, we're drawing white. So these two objects, when their surfaces touch each other, they will exert a force on each other. Okay, so one force is exerted from the blue to the white object, another is exerted from the white object to the blue. This is what we call as contact force. And as you can see, this is actually an example of Newton's third law, which I presume you've learned in high school, right? Newton's third law, where every action has an equal, okay, but opposite reaction. Opposite reaction. Okay, this means that the force that's exerted by the blue object to the white object due to contact force has the same value as the force exerted by the white object to the blue object, meaning, for example, this was 50 newtons, right? This is also 50 newtons as well. but the direction of the force is opposite and the body that they're acting upon is the opposite, meaning that the force from the blue to the white object is going downwards, whereas from the white object to the blue is going upwards, right? So that's the thing about Newton's third law and contact forces. So in the case of our bracket right here, okay, let me just let me just make it a yellow arrow right here, okay? So in the case of a bracket right here, our bracket is subject to the contact forces by the screws, okay? It's experiencing the contact forces by the screw, which I'll be marking in orange, okay? So to show this is the contact force by the screw, this is also the contact force by the screw, okay? And the screw themselves, they are also experiencing contact force due to the bracket, okay? So it'll be acting upwards on the screw's head, okay? And the value here, okay, let me call this FA, and this is FB, is the same. FA is the same as FB. The only difference is the direction and the object that FA and FB are acting to. In this case, FA is acting to the screw, okay, whereas FB is acting, FA is not acting to the screw, my apologies. FA is acting to the bracket, okay, FA is acting to the bracket, whereas FB is acting towards the screw, okay? So that's the only difference actually, like the body that the contact force acts upon and the direction, but the value is essentially the same because it so obeys Newton's third law actually, alright, which I've assumed that you've already learned in high school. Alright, so let me just erase this stuff right here. Okay, let me just make the brush a bit bigger so that'll be easier to show the component. Okay, that being said, right, let's make the brush back to normal. Okay, so yellow, okay, green, okay. So as you can see, our bracket here, alright, as I've already mentioned earlier, it already has contact forces, right? It has a contact force acting on one side by the screw and other side by the screw as well. Now what sort of happens is that at this particular point, which I'm going to highlight in blue color, at this particular point, it's going to experience something interesting. It's going to experience a turning effect, okay, due to something called moment. And this turning effect is caused by the contact force. Okay, I'm gonna make it white, okay? Contact force, which have a certain distance towards the edge that I've marked in blue color, okay? Right? And this is what we call as a moment. So moment, essentially, if I were to define moment, it is the product of the force and distance of line perpendicular to the force. Perpendicular to the force. Okay, so if I name these contact forces here, for example, I would say this is FA and FB, okay, and there is a certain or a fixed distance between the point I've marked in blue, the edge of the bracket, and the force itself, okay. You'll create a moment actually. You'll create a moment, which I'll probably highlight this in, let's see, I'll choose another color here, maybe pink. I think pink would be easier to visualize. Yes. So you would have here the moment of M1, and you would also have here a moment of M2. Okay? So this will create a turning effect on the bracket itself. Okay? This will create a turning effect on the bracket itself. Alright? And from the perspective of the edge of the bracket, it is kind of like in a tug of war actually. If you guys are familiar with a tug of war, let me just draw a simple example of a tug of war. So you have, like, say for example, two kids right here, kid A and kid B. Okay, I'm gonna name that as A, I'm gonna name that as B, And let's say you have a rope. Okay, let's say you have a rope. I'm gonna probably draw this in a white color. They're holding a rope. Okay. Okay. And kid A is obviously, as you know, in the tug of war, he's gonna have to go that direction, and B's have to go in the opposite direction, right? So as they keep pulling, eventually, at some point, okay, assume that both A and B have similar strength, or similar, they're both of equal strength when pulling the rope. What would happen is that the rope actually would stretch. Rope would stretch, right? The rope would stretch until it breaks, right? It will stretch until it will break, right? Because A will be pulling it this side, as strongly as he or she could, and B also will be doing the same. So the rope would stretch until it breaks. The rope would actually be kaput, right? It'll be gone. It'll be something like this. It'll be more of a. Let me just draw it right. Sorry about that. It'll be more like this. So, yeah. So this is how the rope would be, right, after the tug of war. Likewise, if we're talking about the bracket, you will also experience failure. Okay, you'll experience failure because of the two turning effect, or the two moments acting on the bracket itself. So eventually you'll come to a point where the bracket will start to form a crack. Okay, it will start to form a crack. Okay, let me just draw it here. Okay, and let me just highlight the moment in pink. Right, so you have your M1 and you have your M2, and I'm gonna draw the crack in orange color. So eventually the bracket will start to experience a crack, and that automatically means that the component has failed. And it's no longer usable, because if the bracket is actually cracked, it can no longer support the other components. Actually, for example, if you're talking about your chair, the bracket can't support the chair anymore because the bracket has already failed, right? And this will be very dangerous actually if it has actually failed, because then it can cause injuries to the user. For example, in the case of the chair, right, if you have a chair right here, for example, right, and then someone was sitting on this chair, let's say I have a person sitting on this chair, okay, I don't know a good drawing, but anyway, and the brackets are used to secure between the seat and the legs. Now if the brackets were to fail, of course this will result in the chair falling, right? One of the legs would be gone missing, the person would fall down and would get injured actually, right? So this is not a good sign. This is definitely not a good sign. And now you might be wondering, how can the bracket fail? How can the turning effect caused by both M1 and M2, as I've highlighted earlier, make the bracket fail? Like, how is this possible? I'm glad you asked, because there is something interesting that's going on inside the edge of the bracket. Okay, let me just erase that and show you what I mean. Right, let me just choose green. Okay, so what's actually happening at the edge of the bracket? Okay, if I were to, let's say, do a section, if I were to cut the bracket like with a thin knife, for example, imagine it was like a cake and I cut it with a thin knife across this diagonal that I'm drawing right here in red, that touches the edge of the bracket. What really happens is that there's something quite mystical going inside the bracket. Okay, there's something very mystical about it. Okay, so let me just draw the moment turning effect at M1. Okay, M1. Okay, and this bracket also has an internal moment inside it. Okay, it has an internal moment along itself. Let me just call this I'll just call this M3 for now. Okay, so this is what we call as an internal moment. Alright, and this internal moment is very frequently common in all materials actually that's experiencing turning effect. Inside the material there will be this internal moment which actually happens in the material itself. In the material, yeah. itself. Okay, and this internal moment is actually a byproduct of these very tiny forces, or tiny forces actually, that is acting on it. Okay, that's acting on the material itself. Okay, these tiny forces, actually I wouldn't really call them forces, it's more of the force per unit area. Actually, that's the correct definition of these things, which we would call them as stress. Okay, we'll call them a stress, which is the relationship between the force, all right, internal force actually, specifically experienced by an object. So I'm going to write this as internal, okay, over the cross section area. In this case, our cross section area would be the section of the bracket itself. Okay, the section, oops, sorry, right, section of the bracket. Okay, so that is the what we call a stress. Okay, all materials go to the stress, by the way, they all experience the stress actually. So this is a very common phenomena. And before you might say, wait, isn't it similar to the formula for pressure? Pressure is also just force over area. And I would digress and say no, stress and pressure are completely different. Okay, stress, it's more of a mechanical thing that happens inside materials, whereas pressure is basically the force that is just exerted per unit area of a surface. For example, maybe like in a fluid, or like in a fluid, for example, like a liquid. Okay, let me just draw that in blue color. Okay, let's say for example you're inside the water, right? You're here, you're swimming. Okay, all right, what you're feeling, okay, what you're feeling that's acting on your body is actually pressure. Okay, which is dependent upon the force, right? The force, which is basically the weight of the water itself, which is the weight of the water molecules. Okay, the weight of water molecules. Okay, the weight of water, I'm just gonna write water right here, over the area, which the area in this case is basically your body. So this is just your body. Okay, so that is the difference mainly between pressure and stress. Okay, it's a bit different actually, even though I know the formula is the same and the units are the same, but the purpose is completely different. For materials, actually, we always talk about stress, we will not talk about pressure. And maybe I might delve into this another time, but just know for now that stress and pressure are completely different things. Okay, so as I said before, this bracket develops stress, right? And this stress right here, okay, is responsible, okay, let me just change this to yellow, by the way, is responsible for what? It's responsible for deforming the material, for shape deforming, right? Deforming meaning that it changes material, right? So it sort of changes materials. Okay, changes materials, what you call it, shape, right? So it changes the material shape or size as well. Okay, it can change material shape or size, right? And one thing to note is that this bracket, which is normally made out of steel, okay, it's normally made out of steel, has a limit, you know, of how much deformation it can take. So it has a limit of how much deformation you can take, of how much deformation, okay, it can take, right? So it has a limit actually. And if the stress that I've highlighted here, the stresses that developed on the bracket itself, tends to exceed, or tends to be more, let me just, yeah, tends to be more of the material's limit, of the material's limit, right? What would happen? A crack will form, and material will fail, and the component would fail. Okay, so the component fails. Okay, so the component will fail, and that is not what we want. So we must, as engineers, try to keep this stress, okay, this stress lower than the limit of the material itself. We don't want to keep it higher. If you keep it higher, then obviously the material will fail. Or if we try to keep it as close as to the limit of the material itself, we also don't want that, because it might cause the material to fail as well. Okay, so that is the job of engineers, actually, like how we try to minimize the stress value, right? How do you try to minimize the stress value? In case if you're still a bit lost, you can think of this analogy like this. Actually, I know this might be a little bit of a dark analogy, but let me try to give you a simple example so that you can follow through. Okay, so let's say this is you. Oops, let me brush better. This is you, okay? Alright, and let's just say you're an office worker, okay? You're working at your PC. Alright, my apologies, it's not a very good PC. I can't draw a nice one again. Right, so this is your keyboard, your CPU, your mouse, which we connect from the CPU. I forgot your table, but yeah, you also have a table as well. Nice table, nice desk. Right, and a chair. You have a chair too, okay? Right. So you're working the typical 9 a.m. to 5 p.m. routine, right? You're working from the 9 a.m. to 5 p.m. routine. And obviously in your job, you'll end up having stress, right? There will be stress from your job. Maybe could be your boss, right? Maybe your colleagues, okay? Or maybe your friends and family, right? Your friends and family could also contribute to your stress, right? Contribute friends and family, right? Stress is very normal actually in human life, by the way. Now, remember, you are just a human. You are just a person. There's a certain limit that you can handle, a certain limit of stress you can handle, right? Before it spirals out of control. You can handle, right? The limit of stress that you can handle. And if, let's say, the stress due to all these things combined, the stress is more than your limit, what happens to you? What would actually happen to you? Obviously, you would lose control, right? You would lose control of yourself. Lose control of yourself, and you'll end up mentally depressed, for instance. Okay, you might end up mentally depressed actually, right? And your physical health also will be affected. And physical health is affected, right? So just like you trying to deal with stress, right, and also trying to keep in manageable limits, we as engineers must also do the same whenever we're designing with the materials, for example, like this bracket that we talked about earlier. Otherwise, if the stress that's experienced by the bracket is far more than the limit that's allowed by the material itself, then the bracket will fail, and this will cause a lot of problems actually. The parts will fail, the component will fail, and then this can cause possibly millions and millions of dollars, especially if you're dealing with very expensive industries, for example, like aerospace or an automotive, right? Because a simple component failure can cause lives to be lost actually. So this is a very important thing to take note of. So how do we engineers actually reduce the stress levels? Okay, so let me just make this eraser a little bigger. Okay, let me just erase it for a bit. Okay. So one of the ways actually that we engineers would actually sort of reduce the stress level is in improving the design of the bracket itself. So as I've drawn the bracket earlier, okay, you can see, okay, if I highlight this in white, okay, you can see that there's this very sharp edge right here. There's a very sharp edge, okay, and normally this sharp edge is not a good sign, because sharp edges, okay, are typically prone to failure. Very sharp edge makes a component easy to fail, I'd say. Make component easy to fail. Okay, why would it make a component easy to fail? Because if we look at a sharp edge, for instance, okay, what actually happens, okay, so let's just take this color red, okay, so let's talk about M1, right, the moment right here. I'm going to take a section of the bracket itself, and I'm going to draw this with stress. So what happens is that when you have a sharp edge, it tends to maximize the stress at the section itself. It tends to maximize the stress level here, right? It tends to maximize the stress here. The stress would exceed a lot, and this is a bad thing, because eventually it will definitely reach the limit of the material itself. Limit of material itself, right? Itself. And of course will cause the component to fail. So that's why what would engineers normally do, okay, engineers would let me just draw this again. So engineers would normally redesign the bracket. Instead of having a sharp edge, they would make the bracket a bit more rounded. Okay, so the edge is slightly rounded, which is quite typical actually right now, and it's, I think, something you'd see in most modern brackets right now. They always have this round edge. Okay, so round edge. In engineering, we call this a fillet, right? A fillet or a fillet, not fish fillet, by the way. Yeah, not fish fillet. So this is not fish fillet like how Gordon Ramsay does it. It's a fillet that is a rounded edge, okay, which is meant, okay, meant to reduce the stress levels at the bracket itself. So if you have a bracket with a fillet, okay, what happens is, as you section it, right, the stress levels will actually reduce, so become much less now, right? It become very low levels. So this is very good, because ideally we want the stress levels to be as low as possible when we are loading the component itself, so that the material itself will not fail, right? So that means that we want the stress to be less than material limit. So one of the ways how engineers do that is to introduce a fillet to the component itself, right? To introduce a fillet, not fish fillet. Yeah, this is we're not trying to introduce that. Okay, we want this fillet right here. All right. Another way actually, and engineers could reduce the amount of stress experienced in the bracket itself, is to introduce something, right? It's not really a sharp edge, I'd rather say it. It's more like this. Okay. I know it looks a bit weird, but sorry, it looks a bit weird, doesn't it? Okay. Okay, this. What is this thing I just drew up here? What is the slope actually? And this is what we call as a chamfer. Okay, a chamfer. So it's basically a 45-degree slope. Okay, 45-degree slope, and the purpose is exactly the same as the fillet, is to reduce the stress concentration actually at the edge of the bracket itself, to reduce the stress concentration along this area. Okay, because once you reduce the stress concentration here, okay, once you reduce the stress concentration here, again, that means the stress will be less than the material limit itself. So therefore, this bracket will not fail, right? Thus making the bracket safe to use for long periods of time. So this is a very brief walkthrough on how material failure occurs and how it can be avoided actually. Now if you guys are interested to know more about it, I could do a second video on it. I could probably explain a bit more on the stress that is formed inside the bracket itself and what kind of stresses are present in the bracket itself and such, right? So this could be another video topic. Once again, thank you for watching, and I hope this has been a very beneficial lesson to you guys. All right, take care.